Look at today using formulas to solve problems. This is right in line with the stuff we've been doing the past few days. Why don't you go ahead and click and close, put all distractions away. And I think there hopefully will be a little bit of time left over for you. So what we really want to be able to do today, we want to be able to do two things. We want to be able to solve a formula for a specific variable, and that's just using inverse operations. We'll look at an example or two. And then apply formulas to solve some problems, some applications. So what are the steps here? If we're solving an equation for a specific variable, for a specified variable, what are some things just in general we want to do? Okay, and this is right out of your textbook. We want to clear fractions when possible, right? We've already talked about that. That makes things much easier, the algebra much easier if we clear fractions. We want to, use the distributive property to remove grouping symbols, but this is just part of inverse operations. Do you have to memorize these steps? No, you're just clearing fractions and using inverse operations. All this stuff falls under the umbrella of that trick I showed you yesterday or the day before, right? Where we're just reversing the direction of the order of operations tree. Steps 2 through 5. Okay, it's there if you want to look at them, but really just remember inverse operations. So here's an example. What about something like this? What if we're supposed to solve this formula? And why is it a formula? It's only a formula because it applies to something. Like this is the area of this must be area of a trapezoid. Okay. So we're just area of a trapezoid where the two bases are capital B and lowercase b and the height of the trapezoid is h. Do you need to know that? No. But that's why it's a formula, because it applies to something specific. So we want to solve this formula for B. Okay, so what would my steps be to solve for B? And there's not just one way to do this, but maybe we'll arrive at sort of the most efficient way of doing this. Not to say there aren't other correct ways. What do you think? Ideas? If I want to solve for B, lowercase b, let's circle that. So that's the variable right there that we're trying to isolate on the right side of the equation. Okay. Okay, good. So first of all, we're trying to isolate B, so we want to use inverse operations to get it by itself, don't we? I can point to a single B, so I don't really have to do any simplification. Now, on here, they tell you use the distributive property to remove grouping symbols. So they would say distribute the 1/2 and the h. I don't agree with that. You can, but I think there's a better way to do it. If we look at our PEMDAS tree, that's not really what inverse operations tell us, right? We're going in that direction if we're isolating, aren't we? Inverse operations. So is there anything, now when we see this addition and subtraction, is there any addition or subtraction to undo? Well, there's some addition, but how come that one's not, we don't deal with that right away? Why is that a later step? Because it's in parentheses, right? So really what this is telling us is undo addition or subtraction outside of parentheses, right? Because parentheses, if we're doing inverse operations, we don't get to the parentheses until the last step, right? So is there anything outside of parentheses that's being added on the right side that we need to undo? No, right? There's no addition or subtraction outside of those parentheses, so we can skip up. What about multiplication or division? Yeah. What's being multiplied? Give me an example of one thing that's being multiplied outside of the parentheses here. The h. What's another one? The 1/2, exactly, right? So if we want to, the first thing we'll do then is we want to undo the multiplication. Whoops, we're going to undo the multiplication and, oh, what's this doing? The multiplication and division. In this case, it's multiplication. Now, you know what? These are the steps they follow. We'll see if we can, okay, yeah, they did that right. Okay, so we're gonna undo multiplying by 1/2 by multiplying by 2. How come we don't divide by 1/2? Well, we don't divide by fractions, right? Dividing by fractions is confusing. Anytime you're dividing by a fraction or you want to divide by a fraction, you just multiply by the reciprocal, right? So to undo multiplying by 1/2, we just multiply by its reciprocal 2. So there's step 1. Cancel out the 1/2 from the right side. Okay, what's next? Well, you guys already told me, right? We're going to divide by H, right? Get rid of that H. Okay. Now, they distributed. Can you do that? You can. That's fine. We could distribute the H, and that changes a little bit what we do. What I would have done instead, so let's kind of move over to the side here. What I would say you do here is this, right? And what you guys told me, what you would say also is we divide each side by H. So that's going to give us 2A over H equals B plus B. I don't need those parentheses anymore, do I? Because now there's nothing to distribute, so I can just get rid of them, right? So what would our last step be then? Subtract a capital B, exactly. So we would get the answer, if we're strictly following inverse operations, we would get lowercase b equals 2A over H minus capital B, and that's fine. Okay, they chose to distribute the H. Is that wrong? No, it's fine. It's okay to do. So what would they do next if we're trying to isolate that lowercase b? Subtract the BH. Good. We got to subtract before we divide then, right? Okay. So we'd subtract the BH, and then last step, divide by H. Okay. So they get that answer. We get that answer. Are they the same thing? Yeah, they're fine. They're fine. Okay. Make sense? Okay. All right. Questions on that? Okay. Okay, so now let's apply a formula. This is a really common application of formulas. So we want to calculate interest. So I want to go through this example together, and then you're going to see one or two of these on the homework. Here's our formula for the value of an account, the amount of money in an account, if it's accumulating interest, R% interest, right? So R stands for the percentage uh, percentage of the interest rate that they're paying you. N is the number of compoundings per year. What does that mean? Everybody know what, like when they talk about compounding interest, what does that mean? Like if you put money in the bank, what happens? You put money in a bank account, they save your money for you, but they also pay you a little bit of interest for the value of having that money invested in their bank, right? So what does compounding mean? Anybody know? Okay, yeah, okay. So paying you interest, right? There's gonna, like, if it's compounded biannually, right? So if it's compounded twice a year, then that means that that 2 times a year they're going to calculate the amount of interest that you've earned and put that into your account, right? If it's compounded monthly, then that means every month. So 12 times a year they're going to pay you a little bit of interest. And every time they pay you interest, what happens to your principal, the amount of money you have in the bank? That's going to go up a little bit, isn't it? So next time they calculate how much they pay you, it's going to be a slightly bigger chunk because now they're calculating the interest based on more money each time, right? So that's why investing, makes sense, right? It's if you invest, if you guys were to, I know this, everybody, you've probably heard this 1,000 times. If you guys could somehow manage to invest, like even if you just invested $1,000 in a fairly aggressive type of an investment, like a mutual fund or something right now, that would be worth a lot when it comes time for retirement. There's something called the rule of 72, which just says that if you divide whatever the interest rate is, or 72 by whatever the interest rate is, that gives you the doubling time of your investment. So if you were going to make a long-term investment, it's not unreasonable to think you might get something like 12% interest on it, if you're going to leave it in there for a long time. Sometimes that'll be a lot lower, sometimes it'll be a lot higher. But think about that. By the rule of 72, 72 divided by 12 is 6. Every 6 years, you would be doubling your investment. So if you could somehow manage to invest like 5K, Think what that would do. In 6 years, that's how much? 10K, right? In 12 years, how much is that? 20K. 18 years, 40K, right? 24 years. Where were we at? 40? So now it's 80K, right? And you start, if you can hold on to that for like 40 years, which is reasonable, I mean, that starts to push up towards like $1 million, right? I mean, so it's hard to think in those long terms like that, but I mean, if you could manage to do that, man, later on in life, you would really thank yourself. Um, but I digress. Okay, so P is the principal, the amount you're investing. R is the interest rate as a decimal. N is the number of compoundings, and T is the number of years down the line. Okay, so let's look at an example here then. How about this? If somebody invests $10,000 and plans to place all the money in a savings account that pays 5% interest compounded quarterly, okay? Uh, help her son go to college in 3 years. Sounds like a good plan. How much money will be in the account after 3 years? Okay, so what are the numbers we're going to be plugging in here? Here's our formula. We really just need to figure out the values of, and we don't have to do anything fancy here because we don't have to solve for a variable because already A is what we're looking for. A is the amount in the account, right? So A is already isolated. We just have to figure out what numbers are we going to plug in before we chug the numbers and get an answer, right? Okay, so what are the numbers we're inputting then? What's the value of P in this case? 10,000, right? That's the original amount, the principal. So P is 10,000. What is what is R? Okay, it's 5%, but we got to make that a decimal, so that would be okay, right, 0.05. What else do we need? We know what T is. What's T? 3, because we want to know how much is in there after 3 years when T equals 3. And then here's probably the tricky one. What's the number of compoundings per year that makes sense? Because if it's compounded quarterly, that means it's happening 4 times a year. So n equals 4, and now it's just a matter of plugging all that stuff in and calculating. No big deal. Okay, so if we plug all that in, what happens? Well, first we got to understand the problem, right? I guess we'll go through all the steps here. Read and reread the problem. Okay, we know what we're doing. There's our formula. Now we have to know what's being plugged in. Okay, we already reviewed that. So if we plug all that information in, what are we getting here? Okay, well, we already said this, right? So we know we're going to end up with, this is the information that's plugged in. If I simplify this, right, there's my A, there's my R, there's my N times T. What do I get? Okay, well, that becomes 0.05 divided by 4 is 0.0125. If I add that to 1, that entire number that's inside the parentheses, the number that's being raised to a power, is 1.0125. Now, as long as that number is bigger than 1, do you see that this is going to be helpful to us, right? Because if you take a number bigger than 1 to a power, you end up with a number bigger than 1, don't you? Right? Okay. So if we plug this in a calculator, you don't even have to write this in steps at this point. Even at this point, you could just input this entire thing into Desmos or into your TI-84 and kick out a number. In fact, that's the best way to do it. You really don't want to do problems in steps like this, because if you do, that number right there, is that exact? It's rounded, isn't it? You're going to have to round it to some degree when you do this in steps. And if you're rounding steps along the way, you're accumulating error. That's called propagated error, right? Every time you round, you're going to make things slightly less exact, right? And so that's going to change the answer from the exact answer. So what's always better to do is just plug all the numbers in at one time and hit go. And then you don't accumulate all those intermediate rounding errors. You just get a final answer. And sure, you're going to round the final answer maybe, but then you're only rounding once instead of multiple times. Does that make sense what I'm saying? Okay, that's especially important when you're in like a science class, like chemistry or physics or some biology or something like that. You don't want to do all these successive rounding. Just do it one time. So what do we find? Okay, well, that's pretty good. She made, $1,600+ by investing that money. That helped. Okay, make sense? Questions? Pretty straightforward. Okay. All right, how about one like this? So the fastest average speed by a cyclist across the continental US is 15.4 miles per hour, average speed. That's pretty fast. If he traveled a total distance of about 3,107.5 miles at this speed, find how long it took him. Okay, and then we want to write the answer in days, hours, and minutes. So there's a lot of stuff going on here. The math isn't horribly complicated, but we got to deal with these units too, so that's good practice. So talk to me. What are we going to do first? Say that again. Okay, so we're coming up with a formula, right? We need to know a formula. So what's the formula that's going to relate? Oops, I didn't want to do that. What's the formula that's going to relate distance and time and speed? Well, it's that one right there, right? Distance equals rate times time, or maybe you might remember it like this. Either way, it doesn't matter. Maybe you remember it as rate equals distance over time. Doesn't matter. Same thing, right? So there's the formula we need. What is it that we're trying to solve for? How long? So that's going to be time, t. Okay, so we got to isolate the t, right? If we isolate the t, we get, oh, actually, so we could do this two ways. So you could algebraically just isolate the t and get t equals d over r if you want to. That's fine. And then plug in the values. Or you really don't even have to do that. We could plug numbers in right away and then isolate the t. In this case, it doesn't make much difference because the algebra is pretty easy. But if it's a very complicated formula, like for example, this last one, if we were trying to, for example, solve for like r in this one or something, it might have been a lot easier to plug the numbers in first because it's easier to combine numbers in isolated variables sometimes than it is to do all that algebra on individual variables, right? So if you're doing a problem like this, you always have the freedom. If I know I'm solving for t and I can plug numbers in for everything else, just do it. Plug the numbers in and then isolate the t, okay? So if we do that, we know that the distance is 3,107.5, r is 15.4. What do we get? Okay, well, we get that answer, right? If I plug the numbers in, and then it's pretty straightforward. Just divide each side by 15.4, and we got it. Okay. Now, what is that though? That's going to give us an answer as a decimal. So interpret that. What does that mean? Okay, so 201.79 hours, right? Okay, that's correct, but is that specifically what was asked for? Okay, they wanted the answer written in terms of days, hours, what do they want? Days, hours, and minutes. Okay, so how would I do that? Okay, so we're going to need some some ratios here maybe, right? Now, I'm going to show this to you in a way that's maybe a little bit different than what the book does. Because my background's in physics and I've always taught physics in the past. Uh, I want to show this to you kind of from a science teacher's perspective. When you want to change units, you always use things called changers. And you guys are not in chem yet, correct? Oh, are you in chem this year? Okay. Juniors chem? Okay, I got you. Okay, so some of you may have seen a little bit of this, some of you may not have, but this is a really valuable thing to be able to do. So if I want to end up with hours, minutes, and seconds, we're going to do this. We've got 201.79 hours, right? We already have the 201 hours part, don't we? Okay, we need to take that 0.79 hours and turn that into, oh, we haven't done days yet though, have we? Right? Okay, we need days. Okay, so the 201, we're going to have to take that and convert that to days. So let's do a little side work here. 201 hours, if I want to convert that into days, I'm going to multiply by a changer. The unit hours starts off on top. So what I always want to do, I want to cancel hours and replace that with days. We have to have some unit of time on top. We want to transition from hours to days. So which unit in my changer? My changer is going to involve the unit I start with and the unit I want to end up with, hours and days. Which one has to go on the bottom? Hours. How come? Because we want them to cancel. So we want hours on the bottom and days on the top. We'll just call D is for days, I guess. Okay. So now what I need to do in the changer, we've talked about our properties of real numbers. What was our multiplicative identity? What's the number we can multiply by and not change the value of something? 1. So this has to be 1. We want 201 hours to not change. We just want to change the way we express that, right? So if I want this changer to equal 1, then I need to have the same unit of time on the top as the bottom. So typically what you do is you're going to start with the bigger one of the two, which is days. 1 day would equal how many hours? 24. So there's our changer, right? Does that make sense? Now look what happens. The hours cancel. And if I do the math, if I multiply straight across, I just get 201 over 24 days, right? Okay, well, what is 201 over 24? Somebody crank that out on your calculator. What's that give us? Okay, and that's a terminating decimal, isn't it? Right? If it's a terminating decimal, just leave it as a decimal. Now, if it's a repeating decimal or it goes forever and has no pattern, then we probably want to make this into a fraction instead. Okay, but the fact that it's a terminating decimal means we can just leave it as a decimal. It's fine. What was it again? I'm sorry? 8.375 days. Okay, so how many days did it take then? 8 days plus some additional time, right? So for our final answer, the time is going to equal 8 days. Now we need to figure out the rest of this, right? So we had 8 days and we have this additional 3.375 days, which we need to, what do we need to do with that? Turn it into hours, okay? So how am I going to turn this part, whoops, how am I going to turn this part into hours? Okay, I'm going to multiply by a changer. This time it's going to be the reciprocal of that changer, isn't it? So we're going to take 0. Oh, by the way, this was in hours, right? 0.375 days times, this time I want days on the bottom, hours on top. 1 day is 24 hours. So 0.375, that's 3/8. So that's going to be, what, 9? 9 hours? Is that right? Double check me. Oh, yeah, that's right, isn't it? 9, okay. 9 hours, right? The days cancel. So I get 9 hours, but I've got this additional, let's see, I've got this additional 0.79 hours that we never used, right? Remember that? So we're going to have to combine that with that. And now we know that we've got 8 days and 9.79 hours. Okay, give me thumbs on so far. We good? Okay. So we need to come down and do 9.79 hours. We have 9 hours, but I've got this additional part, this 0.79, that I've got to convert into what? Minutes, because we don't want decimal values, right? So let's just do this. Oops. So 0.79 hours, I'm going to multiply by another changer. What do I want to end up with? Minutes, okay? So minutes goes on top. What goes on bottom? Hours. What's my changer going to be? What numbers go on top and bottom here? 60 goes where? Top, okay, because there's 60 minutes in 1 hour. If I multiply straight across, look, the hours cancel. What's that give me, everybody? Somebody. 47.4. Okay. So what have we got then? Well, we've got 8 days. We've got 47 minutes. We've got 9 hours, right? And let's even go one step further than they did. Let's go down to seconds even. I've got this additional fraction of a minute, 0.4 minutes. What would I want to do with that? Okay, I'm going to multiply that by a changer. Good. I want minutes on the bottom, seconds on the top, and 1 minute is how many seconds? 60. So what do we get then? Oops, okay. The minutes cancel and I get 24 seconds. So what's my final answer then? Well, I get 8 days. How many hours was it? 9 hours. How many minutes? 47 minutes and 24 seconds. Okay, make sense? Okay. All right. One more I want to go through. One like this. This is a good question. We'll see this again, something like this in calculus, asking better, more complicated, more interesting questions. But for now, we've got this, this pill-shaped liquid hydrogen tank. You've all seen those on the back of trucks before, right? So if the ends of the tank are hemispheres and the volume of the pill-shaped tank is this big, that's supposed to be cubic meters, 1,507.36 cubic meters, find the value of X to 1 decimal place, okay? So what would we do with this one? This is pretty challenging. What do you think? Okay, how could I come up with a total volume for that pill-shaped tank? This is really useful to do in math. Is there a way that I could kind of cut and paste that to make it look? Okay, so I could take the end caps off and combine those to make a sphere, right? So the volume of the end caps combined is the volume of a sphere. And then how would you describe that middle part? What kind of shape is that? Good, cylinder. Okay, so then we get the volume of the cylinder. If we add those up, we get the total volume, right? So let's think about this in terms of formulas, right? Do you remember what's the volume of a sphere? That's the area of a circle, right? It is, yeah. 4/3 pi. Okay, now what would the what would the power of r have to be? We can think about this and think about this logically. Think in terms of units. What we measure volume in what kinds of units? Cubic units, right? So to get cubic units, I'm going to have a product of 3 different measurements, right? So what would the power of r have to be? It has to be cubed, right? Because radius is going to be measured in like meters, for example. So to get cubic meters, I'm going to have to cube that radius, aren't I? Right? Okay, that's helpful to do that. Sometimes you're looking at like unit analysis like that. A lot of times, if you're unsure, just thinking what would the units need to be and how would I get those units? That helps all the time. Very useful. So there's our volume of the sphere part, 4/3 pi r cubed. What about the volume of the cylinder? What would that be? Mhm. That's it. And how do you remember that? Pi r squared times height. Well, because the circular base has an area of pi r squared. To carve out a volume, we're just going to take that area and extrude it through space. We're going to move it through space by a distance of h to carve out all that volume of the cylinder. It's kind of a way to internalize that and think about how you get that formula. So pi r squared h. Okay, what is it that we're actually solving for here? When we're solving for x, which, that's h, isn't it? Right? H is x. And r, what's r? 4.2, isn't it? And that's the same radius for both the sphere and the cylinder, correct? Okay, so look, we could plug in a bunch of stuff then, couldn't we? This looks very complicated, but if I'm trying to solve for h, look, I know what the volume is, and I know what r is. I plug that stuff in, and the only unknown left is h, right? So what do we get? If we plug all that stuff in, we get 1507.36 equals 4/3 pi times my radius, which is 4.2 cubed, plus pi times 4.2 squared times x, right? Okay, now a lot of times, even our book tells you to just plug in some value for pi, and that's okay. I think they tell you to plug in 3.1416. Hold on, 3.14. Yeah, I think that's what they tell you, 3.1416. I don't have it up here, but just follow the directions when you get to one like this. How could we do this and not accumulate rounding error? It's like we could, like, what would the steps be to isolate x? First, we would do what? Okay, but if I'm trying to isolate, let's write down PEMDAS. We're going in that direction, right? So if I want to isolate that x, what's the first thing I have to do? Okay, there really aren't any like terms here. Multiply, you're thinking multiply by 3 to clear fractions and things? Those are all good suggestions. Let's just assume here, let me preface this by saying at the end, we're just going to plug all this into Desmos at once. And we'll do that together so you can see what that looks like. So if I want to isolate that x, first I have to undo any addition by subtracting or undo any subtraction by adding outside of parentheses. Does anybody see any addition here that's being done outside of any parentheses? How about that guy, right? Look at that. There's an addition sign. So the x is a part of this term right here, right? What did I just do? Oh, okay. Oh, yeah, I did. You're right. Thank you. I never know what I'm doing up here. It's just a comedy of errors. So we've got this term. How many terms are there on the right side of this equation? Show me with your fingers. How many terms? Terms are things that are being added or subtracted. Okay, good. There are 2 terms. Here is the first term. There's a term. Plus that whole thing is a term. Do you see what I mean by that then when I say how many terms are there? How many things are being added? Well, that's one big thing that's being added. It's complicated looking, but still it's just one product of a bunch of things, right? But it's one thing that's being added to that big one thing, okay? So if I've got 2 terms that are being added, the first thing I want to do is get rid of any term that doesn't include an x. So I'm going to subtract that whole thing to the other side. It's going to look really messy, but remember, these are just numbers that I can punch in on a calculator, okay? So it's going to self-clean. It's not like we have to do anything really fancy here. Could we go through and multiply both sides by 3? Yeah, we could. It's fine. We could. But I'm going to skip that step because I know I can just type in a 4/3 on my calculator, okay? So what do we end up with then? Well, we get 15. We get what we already had on the left side, which is 1507.36 minus that whole term, 4/3 pi times 4.2 cubed equals that term, the term that contains the x. Okay, so step 1 was subtracting some stuff. What's step 2 going to be? Divide, because now look, we've got x is being multiplied by all that stuff, right? I undo multiplication by divide. Okay, so I'll just divide each side through by pi times the quantity 4.2 squared. Well, look what happens. That cancels everything on that side except my x, so I got it isolated, right? What's it equal to? All that junk. But those are just numbers. Look how easy it is in Desmos to just put all that stuff in at the same time. And this is good practice, like for your science classes. Do this in one big calculation. So if I go into Desmos, and we want to calculate that whole thing. Here, let me do this. I'm going to take, just so we can see it better. That's what x is equal to, right? So that's what we're going to calculate. So in Desmos, okay, we'll just put all that in. How do I do that? Well, I'm going to type in 1507.36. What's next? Minus 4 divided by 3 makes the fraction 4/3. Hit the right arrow. I can just type pi. Oops, I thought I could. If it's lowercase, I can't. If you just type pi, you get pi. Or you can go down and grab it from the keyboard if you want to. Oh, man. Okay. We'll wrap this one little bit up tomorrow and then let you guys work.